Hi everybody. When we look around us, a lot of the data is going to be hierarchical, with a clear relationship between a parent and a child. Common real-world examples include family trees, organizational charts, and flowcharts and diagrams, and more. In our programming world, a lot of the data we'll encounter will be dependent on various inputs and outputs that are related in a hierarchical way, could have been determined many sequences upstream of us. And when it comes to representing hierarchical data, there's one data structure that you must always turn to, and that is the tree data structure. And in this video, we're going to get started learning a little bit more about them and really set the foundation for learning more about specialized tree data structures in subsequent videos. So let's get started. By the way, if you want a friendly yet comprehensive look into data structures and algorithms, including this topic of trees, my best-selling book, Algorithms, Absolute Beginner's Guide, is just what you need. Look for it pretty much in any bookstore, online, or in the real world. Now, getting back on track. So when it comes to hierarchical data, we don't have to use a tree. We can certainly represent them using linear data structures like an array or linked list. But the thing is, if you had to eat soup, right? The most common way of eating soup is using a bowl and a spoon. Pretty efficient, makes a lot of sense, right? But you could sort of eat it using a plate and a fork. It might take you a while, but you can still do it. The thing is, you want to use the right data structure for the right task at hand. And I think in this case, when it comes to hierarchical data, the right data structure is the tree. Others can be used, but we really want to focus on the tree. And so if we take many steps back, a tree data structure, we talked about it before, it's just a way of organizing data in a hierarchical manner. And there's a lot of parallels to nature. Trees in our computer world come in many shapes and sizes, and the way we can visualize one is, what you can see on the screen right now. You have a bunch of circles, and you see a bunch of lines connecting each of these circles. Now, this sort of looks like a tree, maybe an upside down tree, but it looks a little bit like a tree. This is the top of the branch and things going down, but there's a more precise terminology we use when describing them. Each circle in our tree is known as a node, and the node plays a very important role in our tree. It is responsible for storing data, and it's also responsible for linking to other nodes. And the link itself, which we visualize as a line, is more formally known as an edge. So your tree is made up of primarily nodes and edges, and the combination of them and the relationship between them forms the basis of how we think data needs to be modeled in this case. There are a few more things we need to keep in mind. The anatomy of a tree is more than just nodes and edges in our world. We have additional labels. We have children, parents, siblings, root, and leaves. And it's important to know what these mean, because when we talk about trees, when we talk about how data is represented in a tree, you'll often see these kind of terms being used interchangeably. And it's really good for you to be able to quickly pinpoint what part of the tree or what part of the data within a branch of a tree is being referred to. So let's start at the top. The easiest of nodes to classify are the children. There are often many children in a tree, and a child node is any node that is a direct extension of another node. So except for the very node at the top, in this case the little yellow node right here, that's known as a root, we'll talk about it separately, all the nodes here fit the description of a child. They are extensions of another node, and you can see that in this case the green nodes are extensions of the blue node, and the blue nodes are extensions of the yellow node. Similarly, the red node here is an extension of this particular green node right here, and they're all children. Now, when you have children, you have parents. A parent node is any node that has children, and one thing to call out is the meaning of parent or children is relative depending on what part of the tree we're looking at. So for example, a node can be a child, a parent, a grandparent, a grandchild, or all of the above at the same time. It is convention to never go beyond referring to a node as just a child, which is a parent. Like for example, this green node right here, it can be many things. It's definitely the child of the blue node, it's a parent of the red node, it is a grandchild of the yellow node. So adding extra familiar layers just adds more complexity, especially since we have different ways of specifying the exact layer in the hierarchy a node is present in. So we don't typically go beyond parent and child. There is one special family relationship though that we do want to call out, and that is siblings. So siblings are all the nodes that share a common parent, share the same parent in this case, and are often on the same level of visual. So you can see all the siblings here are the blue nodes, the green nodes, and the red nodes. You could also kind of make this green a sibling as well, but it's not, because the common parent here is only this. This could be a cousin, in some ways. Now, we're almost done here. Earlier we said that all nodes are children except for the first node at the very top, which has no parent. That node is better known to friends and family and computer scientists as the root. And so it has this special node. This is where all the tree data ultimately starts from. So while the root is a node that has no parent, on the other extreme are the nodes that don't have any children. These nodes are commonly known as leaves. And you can see in their leaves in this case are the blue node, the green node, and the red nodes because they have no children from there. They're the end of the line for this particular branch of tree. So already, at this point, we covered the basic properties of trees and the many names we can give to each node depending on how zoomed in or zoomed out we are when looking at them. There are a few more tree properties and node groupings as special names, but we'll cross them when we get to them later. Now, when we talk about specifically where a node is in a particular tree and how to refer to it, there's a more formal way of describing it using numbers, a very fun type of data type in programming. The two properties are height and depth. The height of a node is the maximum number of edges that we must cross down to reach a furthest leaf node, the current node. These descriptions, I'm reading them because it's how you're going to be seeing them formally described in many textbooks and in classes. But when we look at a visual later on, we'll be able to see what they actually mean in a more easy way. The depth of a node is the number of edges we must cross up to reach the root node from the current node. So depth is really something that, how far away are we from the very bottom of what we're dealing with here. And so here's a much better explanation of what it is. Notice at the very top, our root node, we have a height of 3 because there are 3 layers of nodes before we reach the very bottom of the nodes here. And you can see in this blue node, our height is 0 because I have no children at the leaf node, and all leaf nodes have a height of 0 because there's nowhere further it can go. The height is going to be 0. Similarly, this one has a height of 1 because it's one level of nodes before I reach the last node right here. Depth, on the other hand, it's not really going to be changing depending on what layer of the nodes I'm looking at. It always tells me how far away I am from the lowest node that is currently there. And so something to note is that height is relative to each node, depending entirely on how far away the furthest leaf node from that particular node is. The value for depth is global to the tree, and it doesn't matter what the shape of our tree ultimately is. So between all of the things we saw earlier, parent, child, sibling, root, and now height and depth, you have a very descriptive way, or what's the right word to say it? You have a nice bag of words that you can use to describe any node on any part of the tree. And so with that, if you have any questions or comments, just want to discuss data structures and algorithms with a friendly group of developers who like just to help people out, check out my forums at forum.group.com, where I and others would be very happy to help you out. Before I wrap this up, here's some quick actions you can take to go deeper into topics we talked about or to keep up with all the content that I regularly share. And with that, I will see you all next time.